Welcome back to the lab session. Our today's experiment is numerical aperture and bending losses of an optical fiber. And the aim of the experiment is determination of numerical aperture and bending losses of the given optical fiber. This is our aim. So to do this experiment in our lab, we are using the apparatus, an optical fiber trainer board which consists of an LED which is our light source, and we have a photo detector which is used to detect the light intensity and it converts into its equivalent optical power form. And to measure that optical power, we have the digital optical power meter here, and these are the terminals of our digital optical power meter. Red indicates positive, black indicates negative. And this is the knob, variable knob, which is used to adjust the intensity of our given light source. So by rotating this knob, we can vary the intensity of this given light source. And these are the terminals of our photo detector. Again, red indicates positive, black indicates negative. This is our power supply on and off button. Coming to the other devices we are using, there is a 1 meter length of the optical fiber, 1 meter length of the optical fiber, and we have numerical aperture scale. So the scale consists of various concentric circles are there. So the innermost circle is having the diameter of 4 mm, which already I have measured with the help of my meter scale. This is the innermost one is having 4 mm diameter, the next second one is 8 mm, next 12, and so on like that. So this is the diameter of the circle. And coming to the another device, your numerical aperture jig. So on this jig again you have some scale here. So this is again in meter scale. Each line indicates here 0.2 centimeters. That means 2 mm. So 2 mm, 4, 6, 8, 1, and so on. So this is about our jig. So then coming to the formula. So this is the formula to measure the numerical aperture. First we will discuss about numerical aperture. So what is called numerical aperture? Light gathering ability of an optical fiber. So to measure that numerical aperture, we are using the formula in our lab, W by under root of 4L square plus W square. And you also know this NA is also equal to sin theta A from the definition, right? So now let us see what is called this W and L. Here W is the diameter of the light falling spot on the screen. What screen is that? Your numerical aperture screen. So this is the screen. So W is nothing but diameter of the light falling spot on the screen. Spot is nothing but your light spot. Right. Now coming to the capital L. This is the distance between the optical fiber end and the screen. I will show you that. So this is about our formula description. Now let us start the experiment. So to start our experiment, firstly I am going to connect my 1 meter length of the optical fiber one end to the given light source. So like this I have connected my one end of the optical fiber, and this second end of the optical fiber I will connect to the another device. This is called your numerical aperture jig, right, like this. So I have connected. So after connecting, you just keep like this. Then what you have to measure from this numerical aperture. So for that I will show you the tabular column. So this is the tabular column. So after connecting that, so what are the readings that you need to take from the experiment? You are going to measure the distance between the optical fiber end and the screen, which is denoted with capital L, and also the diameter of the light spot falling on the screen, which is denoted with W, right? So first let me switch on the kit. So after switch on this kit, so this is what my intensity adjustment knob. So to see that light intensity, I will show you. See, the light is falling on my finger, right? Now it is with maximum intensity. Now I have maximum. See, when I am rotating this knob in anti-clockwise direction, it is now completely minimum. Again, when I am increasing, see, this is the highest intensity. So while measuring this numerical aperture, the first point is you need to remember this knob should be with respect to high intensity position. The light intensity must be here high. Then how to take the reading, I will tell you. You need to measure both L and W. So coming to the L, what is L? Distance between the optical fiber end to the screen. So this is what the position. So you need to place your screen on the jig like this. So the capital L is nothing but distance between this optical fiber end to the screen. So this length is called your capital L. So to take this reading, I am just following like this. The scale I have fixed like this. So like capital L is equal to first reading. I am going to fix for 4 mm. Right? So 4 mm means I need to place my numerical aperture scale on the jig for 4 mm. See, on the second line. So like this I have placed my jig. So my scale I just placed for 4 mm. This is what my length, capital L value. So when I placed my scale for 4 mm, I need to observe that how many number of circles are going to be occupied by this light intensity. So for that I need to count the number of circles on the numerical aperture scale. See, completely first, second, third. 3 complete circles are occupied by the light spot which is coming out from the optical fiber. So with respect to that, so each circle has 4 mm now, coming to 3 complete circles occupied. 4, 8, 12. So this is your W value, right? Now likewise you need to go for the second reading. How can you take the second reading? I already fixed for 8 centimeters L. So for 8 means you need to move your numerical aperture scale on the jig for 8 mm. That means exactly you need to place your scale on the 4th line. 8 mm. Again at this moment you also observe that how many number of circles are occupied by the light intensity. So count the number of circles and write the diameter of the circle. So now this time 1, 2, 3, 4, 5. 5 complete circles are occupied here. So 5 4s are 20. Now again I am going to move for 12. So like that you are going to vary your numerical aperture scale on the jig. So in a similar way, measure the L value and measure the W value. So I have already taken those readings before this itself. So these are the readings. So in this book I have started with the 2 mm onwards. For 2 mm I have 8 W value, and for 4 mm L I got 12 W, and for 6 mm L value I got 16 W value. For 12 mm it is 20, and for 18 it is 24. So now with this tabular column you got all the L and W readings, and you substitute these values in the formula. So this is what the formula, W by under root of 4L square plus W square. So after substituting all those readings, so I have done already the calculation. So after substituting all those calculations, I got the readings like that. So for each and every value of L and W, measure NA, and after calculating for all 5 readings NAs, you need to take the average. So this is what my average value of the numerical aperture. I got 0.744. This is the gathering ability of my 1 meter optical fiber for the given light source. And I also calculated the value of acceptance angle. You know the definition of numerical aperture in another way, no? Sine of acceptance angle is also called as numerical aperture. So NA is equal to sine theta A. From that, theta A is equal to sine inverse of NA. So like that you need to measure all these theta values for each and every NA. Finally, take the average of all these 5 readings. So this is what my average acceptance angle for this readings. So that's all for numerical. Another part of this experiment is determination of bending losses of the given optical fiber. So to do this part, we are using the formula loss is equal to P in minus P out. Units are decibels per meter. So in this formula, what is P in and P out? P in is the input power, light which is transmitted through the optical fiber. P out, output power, light which is received from the optical fiber. So coming to the tabular column. So this is the tabular column, required tabular column. So the first column indicates input power, second column indicates output power. So input power is nothing but output power of the optical fiber before bending. Output power is nothing but output power of the optical fiber with bending. Right. So how to do this procedure? For that we are using the same optical tuner board, and again I am connecting this 1 meter length of the optical fiber to the light source by keeping the high intensity with the help of this knob. So this is the high intensity, and the second end of this optical fiber I am connecting to the photo detector. You know the role of detector, which detects the light and whose intensity will convert into optical power form. That power can be measured with the help of this digital optical power meter, whose terminals are here. Red indicates positive, black indicates negative, and these are the terminals of your detector. Red is positive, black is negative. Now to take the readings in the digital output power meter, we need to connect this power meter and detector in parallel. Parallel means positive of the power meter to positive of the detector, negative of the power meter to negative of the detector. Right. Now you can see the power readings in the output power meter. So let us start the experiment. So to do this bending losses, so first reading we are going with input optical power. Input optical power, that is nothing but output power of the optical fiber without bending. For that you need to stretch the optical fiber cable like this. Avoid as much as possible bends. So like this you need to hold the cable. After holding, with the help of this intensity knob, you can adjust one intensity in the power meter. So that is called your input power. So first I am going with any one value you can adjust. So some minus 105.6 or 5. I just fixed that value in the power meter. This is your P in. So I will write here minus 105.5. Minus 105.5. So for that input power, I am going to bend my optical fiber cable. How can I bend? I need another device called mandrel. So with the help of this device, I am going to bend my cable. So like this. So like this, you just bend for one turn. So like this, you hold the cable and note down the reading in the output power meter. So this is what the output power of the optical fiber with one turn bend, that is equal to minus 105.1. Next, for the second time, I am going to bend my optical fiber cable with the help of the mandrel 2 turns. For 2 turns, again note down the power reading in the power meter. It is showing minus 106.2. Write it down here. Next, go for 3 bends. So for 3 turns, again the value changed, minus 108.2. So minus 108.2, write it in the place of 3 turns column. Now for 4 turns. So for 4 turns, you got the power meter reading minus 108.7. Minus 108.7. So I have just taken for 4 bends readings here. So after taking all these readings, I need to do the average. Add all these 4 divided by 4. You will get the mean reading. So after getting this mean, this is what your output power. So how can I elaborate this? So output power of the optical fiber with bending. This is what your P out. Now substitute this P in and P out in the loss formula. Loss is equal to P in minus P out. You will get one value here. So I have already taken those readings. I will show you that one. So this is what with respect to my input power minus 110.8. So these are all bending readings, and P in, P out. The difference I got it here. This is what my loss. So likewise you need to go for the second reading. So when you are going to start the second reading, what you have to do? Again, same procedure. You need to stretch the cable like that and again adjust the intensity knob. Earlier we have taken minus 105.5. Now I will go with the minus 110.5. Any one reading you can adjust, which gives some difference between previous reading to this reading. So now I am going with minus 110.5. So for this input power, again you go with the same procedure. Take the mandrel, bend your cable for 1 turn, note down the 1 turn reading, 2 turns, 3 turns, 4 turns and so on. Write all the readings in the respective places, calculate the mean and P in P outs, do the loss, P in minus P out. So likewise you need to go with 4 to 5 inputs, 4 to 5 input powers and measure the output power. Finally calculate the loss. After calculating all these losses, do the average. So add all these 5 divided by 5. You will get the average loss. So this is what my average loss for my readings, 0.42. The units for measuring the losses are here, decibels per kilometer. And one more point. Here minus sign indicates the loss sign representation, loss representation. Minus sign represents the losses representation. So coming to the result. So finally I will write the result. The numerical aperture of the given optical fiber is average value 0.85 and the bending losses of the given optical fiber is 0.42 decibels per kilometer. No units for measuring the numerical aperture. That's all. Thank you.